In this video, we're going to review how to use the Norton linkage software to generate position and velocity curves for a slider crank. Um, so one thing we need to do first, though, is when you do this, is set the preferences and switch to millimeters from inches, because our dimensions for this lab are given in millimeters. And then I'm just going to open the file that I already have set up here. Okay, so you can see that the crank is at 30, the coupler is at 90 millimeters. The offset is at 0 because the the axis of the slide is going to pass right through the origin, and then it's at a 45-degree angle. The distance out to the coupler point is 45 millimeters, and it's at 50 degrees. So this should look similar to what you would have on your on the box that you're going to use. So so you can see here's the coupler point, and you're going to have to generate the curves, the plots. So just go to next and then plot. And I should say that sometimes you have to be careful with this software. Sometimes if some of the things you select, you don't get the right answers unless you start with the uppermost for the flyout, start at the top one. And so anyways, so if you do that, it seems to calculate correctly. So whether you're trying to do get the tables or the plots, just click on this top one first. Now we want to find the velocity and position of the coupler point. So we can go here, velocity of coupler point, x, y. So it'll be the x and y velocity coordinates, the magnitude, and the angle of the velocity. So this is one of the plots you want. So again, here's the x and y. This one is the magnitude, and this is the angle of the velocity vector right here. And then you're also asked to find the plot of for the angular velocity of the coupler. So for that one, of course, that's theta 3. I'm sorry, omega 3, right? Omega 2 is the angular velocity of the crank, and omega 3 is the angular velocity of the coupler. Okay, so in this particular example, we had set the angular velocity of the crank to 10 radians per second. So that stays up there, and of course, then alpha of the crank is going to be 0 because it's at a constant velocity. That shows you that. And then the angular speed, the angular rotation of the coupler is shown here. You can see it's oscillating back between negative and positive values, which makes sense. And this up here says alpha 4. That actually is alpha 3, right? Alpha 3. So this is the angular acceleration of the coupler. So anyways, that shows you how this is how you can get these plots that you'll need for this lab. Okay, and then each member of your team will I'll just recalculate this. So each member of your team for this crank here, you can see as the crank goes to different positions, should select a position of the crank. And I will tell you that there are some positions that are easier than others. And you could also set this up to sketch up in SolidWorks. And then just as was demonstrated in class, you can use SolidWorks to find the coordinates or the distances for to the center of rotation, the instantaneous center of rotation, and then you can just use MathCAD to make the calculation. So I mean that's what I would suggest that you do is it's easy to sketch this out in SolidWorks, and then you can extend these lines so that you can find the instantaneous center and use driven dimensions, and that way you can get all the information that you need to use the method of instantaneous center. You should be able to do that fairly quickly. So anyways, this gives you just an idea of how to set this up, get the plot, and then you want to do the calculations using the method of instantaneous centers and compare your results to the plots that you got at the particular angle of the crank.